Hi there and welcome back to Triplicate, and today we are going to move on with that radical synthesizer, the Heresy, and we're going to have another look at the player interface. Now we've got a turntable arrangement which works as we want it, pretty near, but we were having problems with our strings, and the problems were the contacts made between these stainless steel strings and these copper strips. The contact was not reliable and it was dropping out, and despite our best attempts in software to cure these problems, it wasn't really satisfactory. So I would like to away with these strings and try something different. I have played with ribbon controllers in the past. I had one of these Diophor ones, but hard to calibrate. We need to say this pitch is at this point, and these things are hard to calibrate, I suppose, like the strings are, and expensive. And I may well try and make one. You can make one using good old sticky tape and pouring carbon dust on it, but I can't imagine it's very reliable and noise immune. So what I thought we would do instead, we would have something that's where you can get the absolute position, because it consists of a series, and this is an expanded view. These would be around 1 millimeter up across, and we would connect them either in pairs or to something on top, and we would have rather a lot of these in the 50 odd centimeters we need for our strings, and we would have some connection to something with an awful lot of inputs, which would give a position out. So I spent quite a long time, did quite a lot of work trying to get this to work. Firstly, I set off looking into a capacitive system whereby you have the pads and you have a thin non-conducting layer, probably with sticky tape over the top, and you put your finger on them, and the capacitance through your finger, you get a signal through. And I decided that was too complicated, because we were trying to detect 3, 4, 5 picofarads. It's really prone to struggling to stray capacitance. So I abandoned that and just had the pads with a reel with a layer of something conductive just above them, and you press it down and it shorts the pads, which was a lot simpler and would obviously work. You know, you're just making a connection. We know that's going to work. But in the end, the problem is that here I have drawn what the pads would look like on a PCB, and this is whatever, about 25 centimeters, about half the length of the actual thing, and I'd have to zoom in. Those are 1 millimeter spaced pads, which was the number I came up with to get a decent resolution, and you've got to connect all these up to something, and that was, I decided, and you've got, if you put each one 5 centimeters apart, which seems reasonable, if probably a little much, then you've got this narrow strip of circuit board to build all the electronics on and wire them all together. And I decided this was just not feasible. So I went back to analog method, basically wires and contacts of some form, and did a load of work on that and realised I probably could get this to work, but for now I'm going to proceed on with the analogue method, and we may, if we have to, come back to this because it's an absolute pig. You've got to, your PCB, you've got to like wire up 500 of these both ways, and ugh, it's an absolute nightmare. So on with the video on the analog side of things, on the designing an improved analog method. So after probably about a week of trying to work on these PCB pad method, shall we call it, I gave up and decided, despite what I said at the start of the video, to have a go at building a ribbon controller. So let's have a look at that. Okay, so I guess we'd have to call this Plan C, possibly Plan C. Ribbon controller plan. So this we have here is a piece of good old eBay cheapo sticky tape, glue side up, with this, which is Lock Ease, which is just graphite powder, which can be bought cheaply off eBay. I got about six of these little bottle things of it ages ago, and I've never got round to doing this and trying this, which is just rubbed in so it's all in the glue. Okay, let's get a meter set to ohms and attach it across there like that, and you can see we have 123.7k ish. And just for entertainment, I have here, so the way this would work, there would be a big run of copper tape over the top like that, and that you would push that down onto the surface of the graphite. But instead of wasting our length of copper tapes, I'm running out of the stuff. I've just got a little bit here. So here we are, here's the meter, and about halfway, let us 58k, about half. So that's good. Okay, so I've always been a bit wary of this because, yeah, I should zoom us right in. You can see it's a bit patchy and a bit uneven. And if I do that, you can see there's copper graphite powder come off on my finger, and I just think, longevity, is this gonna last, or is it gonna wear, like where it's used most, so it's gonna become unlinear? So I've always been a bit wary of this, but the advantage is it consists of sticky tape, graphite powder and copper tape and some kind of spacing, which we could make easily. So I might build one anyway, because we can build it with bits we've got. We don't need to get PCBs made or anything. But let's see how, well, is it noisy for a start? I mean, is there a lot of crackle and fizz and what have you coming in on the signal? So let's try that first. Actually no, since we've got the meter set up, let's try and see how linear it is first. Okie dokie, I've marked 10, 20, 30, 40 and the end is 50 centimeters. I've switched this to volts, the power supply isn't connected up. Okay, so here at 0 centimeters, here we have 0 volts. 0 centimeters, 0 volts. And I've got a ruler here just so to try and place it fairly precisely. So at 10 centimetres I've got 0.818 of a volt. 10 centimetres, 0.81 of a volt. It's not that accurate. 20, 30, 40, 50. So 20 centimetres, I've got 1.66 of a volt. 1.66 of a volt. 30, I've got 2.79 of a volt. 40, I've got 3.68 volts, and 50 is there, 5.00 volts. So that should be 4, 3, 2, 1. So it doesn't seem very linear. I mean, we could calibrate it, but... Okay, so I've plotted out our results here. So here we have the position, that's in centimetres, that's the measured volts, and the expected volts, if it was linear, is the orange line, and we can see it isn't good. And if we take the worst case, which I think is at 40 centimetres, okay, so we have 5 volts along our length in 36 semitones, so volts per semitone is 140 millivolts, 0.14, and our worst error, which is at 40, is 0.32 of a volts, which gives us 2.3 semitones error. So that's why they use these kind of ribbon controllers. For effects, fine if you just want to go wow 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 with it, but if you actually want something precise, it's not good. Oh dear. I think we're on to plan D here. Which brings us full circle, I believe. Back to thin pieces of wire and copper, but we have come up, I believe, with one improvement. Now this copper tape, this is ages old, and it doesn't seem to be particularly tarnished, is it? It's just an end that's got chewed up. And I chose stainless steel for this because it's quite tough. You can put tension on it and it doesn't tarnish. Well, it doesn't, yes, it does tarnish by the way of stainless steel. So perhaps if we turned this over and we had a very fine wire at the bottom and the copper strip over the top, then perhaps we could get that to work better. And why do I say we should do that method? Because putting thin pieces of copper wire is easy to whatever shape and length we like. Just traces on a PCB, and here we have a Bose Speedo bottom board. I've got spare ones. So I've connected 2 bits of wire here and here, and this track goes along here, up here, through the via and to there. So should we actually see what resistance that track is? Okay, so I have 2 leads here going to the power supply, which, you're going to take my word for it, I have put on to 1 amp. So there's 1 amp flowing through this track, and I'm going to measure the voltage between here and this via, because I don't know how much resistance there is through vias. It will probably just complicate the issue. Oh, there's enough current for the power supply fan to come on. So here we go. Okay, we have 135, shall we call it, millivolts. That's pretty stable. 135 millivolts. So we have 135 millivolts. And how long is this track? Well, let's measure it. It goes from there to that corner, and we'll vary approximately here, so we'll call that 34 millimeters. And from here to the via is, call that 55 millimeters. My writing doesn't get any better. Which gives us a total length of 89 millimeters. So we want a resistance per millimeter. Let's have a resistance per millimeter, which is resistance R equals V over I, but I is 1, so the resistance is 135 milliohms. So the resistance per millimeter is 135 divided by 89 gives us, as dear as damn it, 1.5 milliohms per millimeter. Okay, and if we have 500 millimeters, which we do, millimeters gives us a resistance of 758 milliohms, which is 0.76 of an ohm. Yeah, we could work with that. Our amplifiers might need to be a bit better. Now, as I recall, the stainless steel was about 3 ohms. Shall we measure it? Yeah, let's measure it. Okay, from there to there gives us 3 ohms or so. Okay. Which is 4 times more than our copper wire. Okay, well, I thought before we start getting PCBs made up, we would try and build one using just a fine piece of copper wire, and this is 1 strand of this multi-strand hookup wire, which I measured to be about 0.3 of a millimeter diameter. So let's put some current through this and see how much resistance it is. Okay, so got it stretched out reasonably and weighted down, and that's about 50 centimeters worth of it, and got the meter in shot this time. Wonders will never cease. So let us fire it up again, and that's an amp going through that. Let's turn this on to millivolts DC and see if we can get a reading. .300 millivolts, or minus because I've got the probes the wrong way around. 300 millivolts. So that means we have 300 milliohms along here, which is about half what we would have with our PCB track, we calculate. So we're going to move forward and try and make one like that. If it'll work at 313 milliohms, it'll work up at 750 milliohms. So okay, so here we have our we decided not up to scratch ribbon controller attempt, and reuse and recycle on this side. It comes with convenient stand even. This is another length of that wire, held down with 2 staples and wires connected. So what I shall do now, and I've put a layer of packing tape underneath to try and just make this a bit smoother. I don't have any of that nice furniture board with the plastic facing. I'm going to put a layer of this, which is 1mm, because it's what I have in stock, so to speak. Like that. Cut to size and glued down with double-sided tape, which I haven't got a lot of left, so we might be in trouble there. And on top of that we will have a layer of the best of this I have left, which will be stuck to some more packing tape, and that will be it. So I think I'll just build that and bring you back, since it's just a test. It's not going to be like this in the final version. Okay, swift update. I have this 1mm spaces along here. This stuff is, it's called plastic hard, but it's just some sort of plastic that you can get in sheets, thin sheets, and it's just, you can cut it with scissors. It's just useful for doing this sort of job, where you want accurate thicknesses. That's what I use it for. Right, so now we need somehow our copper tape on like that, and a run of that over the top. Okay, I shall attempt to make that up and put it on. Yeah, I'll do it. Save you swearing. Okay, so that's it. It's done. And we'll do a quick sanity check that it's all still connected as we would hope. Okay, we've got connection down the wire, and we haven't got connection between the wire and the string. So yeah, when we press the tape down, we get connection to the spring. So now we're going to connect the string to the power supply and the wiper, I suppose, the tape, do the picoscope, and we'll see what sort of a signal we get out. Okay, so I have a resistor of 50 odd ohms, so that's dropping the current through it to 100 milliamps, because I've got the power supply set to 5 volts, and across the wiper, we'll call it the copper tape, I've got a resistor and a capacitor, and the capacitor is probably a bit big, but there you go. And as you can see by the trace, it's still a bit noisy. That's because the picoscope is noisy as hell. Or I don't think the picoscope is, I think it's just the earth, the computer earth around here that's noisy as anything. Anyway, Let's see how it does. So the picoscope is set to 50 plus or minus 50 millivolts. So if I run my finger up and down, that seems to be alright. If I run off the off piste and away from the string, you see, but that's what you would expect. Okay, so I think at this point I will wire it up to this one of these, that one, amplifier, differential amplifier that isn't used on here, and I will try and get it working with the heresy code and see if it actually works in practice. So here it is, a very badly bodged together string on top of gaffer taped onto my somewhat bodged together strings from before. Wonderful. And I've just removed the originals and connected it round to the string, and that resistor, that resistor, that resistor and that resistor, I don't know whether you can see, have got a resistor in series making the value about 10 times bigger, so there's 10 times more gain because there's a lot less resistance down this copper wire compared to the stainless. So will it work? Okay, so let us fire that up. Can't run Camtasia, as you probably remember, because Camtasia's screen recorder and the amount of processing power this thing uses don't go together. So here we go. So there you go, that sounds smooth, no dropouts. I will have a quick look at the data just to check, but I think we're onto a winner there. Alright, so I have tested this with just my test code in the Heresy. So what you're seeing here, the top row is the raw data from our string, and the bottom trace is after I did my fancy anti-dropout processing on it, and you can see it's pretty good. So I went up and down, and then I went up and down with some vibrato, and then I just sort of stabbed at it kind of thing, and you see the dropout code. Got rid of that there. Yeah. And there was one dropout here. I don't know, that was maybe my finger not staying quite on the string. It was obviously have to be quite accurate because it's only a very thin string. But I am happy with that. Okay, and just to finish off, I have a further thought. So here is our string trace, a little bit of wire. And here is our finger contact. Well, hang on, what if we were to, instead of doing a straight one, which we can fairly easily do on a PCB, what happens if we do a zigzag? I probably exaggerated that. So our contact, finger contact, would be like that, because I did find it quite hard to keep my finger centered on the string and keep it working. But that way we've got, say, 1 centimetre there. It's hard to get off track on that. And if we have, say, 1 millimetre, so for every millimetre we move on, we've actually moved a centimetre, we've actually got a centimetre of track. So the track is actually 10 times longer. So we get 10 times more resistance, so we can either turn the power down or have a lot more signal. So it's also a great advantage from that respect. How you lay this zigzag track out on a PCB for 500 millimeters and 1 millimeter ago, I don't know. That sounds like a bit of work, but I shall figure it out. Okay, so that just leaves us the big question. Now, I was originally hoping to use some kind of a modular approach with 5 identical PCBs in a row like this, because these 10cm square ones are very cheap, and so there'd be 1, 2, 3, 4 strings across, but I cannot see with some kind of a continuous track down there how it is possible to do that without joins and things here, because the track can't go to the edge, so there's going to be like a gap here, so it's not going to be even. So let us see how much it is going to cost. And so instead of 10 by 10 we've got 50 by 25. So here we have our PCB price calculator for 100 by 100 millimeters, and that gives us a grand total with shipping of $9.93, a very triplicate price if I may say so. Let us try instead 500 by 25, which is 1 string, and we order 5 at a time whether we like it or not. So then we get 4 strings or even 5 strings next to each other. Anyway, let us calculate that, and that takes us to $51.77. Okay, which is not quite such a triplicate price, but I think I'd go with it for something that works, whereas at the minute we have something that doesn't work adequately. Okay, well, that is it. I shall now go off and design a little PCB, a long thin PCB, and send it off and get some made, and we will reconvene when I have them, and we will put them together and build them up and test them, and hopefully they will work nicely, and we will have the strings part of the Heresy finished, done, good enough. And the next time we're on the Heresy we're going to, I think, move on with the sound engine and the flip engine and all that sort of stuff, because I've spent ages on this video, and about half of what I did I've just decided against. So that is it for this video. So for now it's goodbye from Triplicate. Goodbye.